Okay, so good morning again. Thank you for joining this lecture. First of all, this course, GIAN course, and this first introductory lecture. So, as you know, we are here to talk about soft matter in physics, in biology, in materials and science, with three a bit more complicated words: programmability, actuation, and reconfigurability. We will be two main lecturers, and for this series, Dr. Subramanian Namboodirivaan Kutu, with the co-organizers of these lectures from the NIT Calicut, and myself, I'm professor at the École Normale Supérieure in Paris. Here are our details, so don't hesitate to send an email if you want to contact us. For this lecture, I consider that we are scientists, but that we don't know anything in soft matter. So sorry if some of you know already everything. And the idea is to be a bit interactive. So I hope you can participate. And if you don't ask me question, I will ask you questions. So in any case, let's be interactive. I think in general, we would like to have something lively. The idea is not to have something that goes in one direction, so don't hesitate to bring us feedback during the lecture, so we have something that is dynamic. So let's go. This is the subject, what we are talking about. The first important matter is soft matter. So in this lecture, one of my objectives is to introduce what soft matter is. And then you will see that we have three specific keywords, which are programmability, actuation, and reconfigurability. And for that will be the objectives of course. Okay, so in this lecture, I would like to both give you an introduction to the soft matter in general, and then more specifically present what the objectives are. So let's start with soft matter. There are two ways of defining a soft matter. First, we can ask what it is. What is it? So we can define soft matter by its components. Or we can think, what does it do? So we can also define soft matter by phenomena and properties that are specific to soft matter. So I would like to start with its components. So let's start. I show you this first slide. And this slide is not complete, so I've shown a few pictures. I can say that these components are in nature. It's also in our everyday life. For instance, in soaps or cosmetics. It's also present in industry. And its key properties are to modulate surface tension, to stabilize interfaces, and they can also self-assemble, like doing what we can call micelles. So what are we talking about? If you don't speak, I don't speak. That's the deal. So what am I talking about now? These are illustrations. They are in nature, in our lungs, in plants, in everyday life, in soap, in cosmetics, in industry, and key properties to modulate surface tension, stabilize interface, self-assemble. What am I talking about? Surfactant, easy, right? So if you, please answer, because otherwise it will never work, okay? So surfactants, right? Surfactants and in general amplifiers, amphiphilic molecules. So I give this here just some examples. This is a complex of protein and surface active phospholipids, common detergents. It can lower energy, so you can create a lot of surface, for example, doing foam. We will see in this talk that we can harness surfactant to do dynamic transport. This is one example of things we have done. We can move droplets to make this heart shape, and they can self-assemble. Okay, so easy. Let's see another component of soft matter. These are some representation. They are again in our everyday life. We can find them in industry, in biotechnology, in medicine. They are also in nature. And key properties is, for instance, they are macroscopically deformable, light, resistant, and they have properties that could be to be adhesive or repellent, transparent or opaque, insulating or conductive. What we are talking about? What? Polymers, right. Easy. Polymers are also a part of soft matter. I give here some example. Mechanical properties are strong, light, and cheap. That's a problem. They are too cheap, so we are using too much plastic because we trash. Why we should trash plastic, I don't know. Why should not we use more? This is, this is the epoxy motif. It's used a lot in epoxy materials. For instance, many interesting glues are made of epoxy, and this is typical soft matter property, adhesion. All the resists, and this is because you can have interaction between this long chain. They are making the architectures of our cells, so the cytoskeleton, you can see here. And also because we can make biocompatible and make this kind of interesting mechanical properties, they are used a lot for biomedical applications, for instance, bioimplants. Okay, so I see you are doing it quite well. So I will make a little bit more challenging because no, I don't put any properties. And you have to guess now what is this new component I am talking about that you can find in this illustration. So what is it now? So what? You can propose. There is nothing to lose. There is nothing to win, but there is nothing to lose. So what could you suggest? Now I can tell you that if I take this shrimp, what I'm talking about is inside the shell of this shrimp. This is what? DNA is what? Is what? Bio. Biomolecule. Yes, but is it biomolecule here inside? Here? Wow, it's touchscreen. Sorry. So it's a these are biomolecules, but it's the common properties of all these objects. So I will. So this is a protein. So I will try to help you. I'm talking about polyelectrolytes. So polyelectrolytes are polymers that carry charge. Can we move this guy? Yes. So they are also polymers, but they carry charge, and because they carry charge, for instance, DNA is negatively charged, protein is negatively or positively charged, and actually most biopolymers are charged. It's quite important because life is made with water, and charge make this polymer water soluble, and they are also highly present in everyday life. For instance, they are the main components of superabsorbing materials, and it's very important for hygienic compounds. Because they are charged, they can absorb a lot of water, and because they are polymers, then they can trap this water. And they are used a lot for water treatment. So they are very important industrial implication. And the key properties, they have many properties, but the two important properties is that first they are water soluble, so they can bring these mechanical properties like rheology that we have seen in the previous slide, like here. Basically, you can bring this kind of mechanical property in your liquid, okay? And this will provide you very interesting rheological properties, for instance. And they are also reservoir of charges, so they are full of charges, and this will bring two main types of property: electrostatic properties and entropic effect. Entropic effect because you have many charges, and this is why you can capture water, because the polyelectrolytes want to release their counter-ions to gain entropy. So this is another important class of soft matter. So here, you see we are going little bit more difficult. So these are beautiful images. Actually, I took this picture yesterday in my guest house. So what I'm talking about now, what kind of component I am talking about now? Dr. Varnakotu, can you help the audience? What is the component I am talking about now? What is the common point of all these images? It's not fluid because this is not really fluid. What kind of components? So we saw surfactants, we saw polymers, we saw polyelectrolyte, and now I'm talking about colloids. You see, we see what is a real professional. So I'm talking about colloids. So colloids is also another important component of soft matter. What are colloids? They are solid dispersion. They are too small to sediment, basically. Okay, so they are usually nano or micro size, and they can have a lot of functions. They can be magnetic, and you can, for example, make these nice fluids. But they can have all kinds of functionalities. And because they are small enough, their thermal energy will beat gravity, so they will never sediment. And this will make you possible to make suspension, and for instance, inks or pigments. And this bring this very interesting colloidal stability. So, you know, sometimes we call it Chinese ink, but in fact it was invented in Egypt maybe 7,000 years ago. And Egyptians were very smart because they took carbon. Carbon you cannot solubilize in water. They took polyelectrolytes. So they took just what I'm talking before. They took polyelectrolytes like from Arabic gum. They mix together, and this polyelectrolyte go on this carbon material. And this carbon materials now becomes water soluble and highly stable. So you can take this Egyptian ink made 707 years ago, and it's still stable. It's black. Okay, so you can disperse carbon in water because of this this stability and this Brownian motions. They have enough thermal energy not to sediment. And they have a lot of properties. For instance, you can find it for drug delivery or catalyst. And what is quite interesting is this colloids. So they have Brownian motion. So Brownian motion, it looks disorganized, but at the same time, they can also self-organize and make that quite interesting assembly. So here I show an example of colloids that organize like a crystal that is dynamic, and we'll see in some lecture that we can make crystals that are alive. And they self-organize, and then they can have collective properties. So if you take a single particle, it doesn't have any specific interesting properties sometimes, but when they are together, they can get some interesting properties, and for instance, colors. Okay, so here you have opale, and opale is just an assembly of silica particles. Silica, if you take it alone, it has no specific interesting property, it's transparent. But if you put a lot of them together, then they can start to make structural colors. So you can have colors without pigments, and this makes these beautiful colors in opale, and you make also many beautiful colors in animals, especially on insects. So it's not pigments. So if I dissolve this insect, I will have no color, but this pigment are due to the organization of the structure on the surface. So colloids are very important parts of soft matter. So this one. So we saw polymers, polyelectrolytes, surfactants, colloids, and this one, what's inside here? So, sorry? Emulsion, right? You saw that I put butter and not ghee. You know, ghee is not an emulsion. Butter is an emulsion. You have water and oil in butter, but in ghee, you remove most of the water. It's pure fat, so I didn't put ghee, I put butter. Emulsion, and is this an emulsion? What is it? What kind of dessert is it? Yes, and what is the chocolate mousse? In terms of structure, is it an emulsion? What is dispersed in what? Speak loudly. There is no problem to say something that is not what I'm explaining. Yes? No, it's chocolate mousse. Ice cream could work. In some ice cream, it could work. So in chocolate mousse, what is dispersed? It's not a liquid, it's gas. It's air that is dispersed in a liquid. So it's a foam, okay? So I have emulsions, I have a foam. So in general, what I'm talking here about is dispersed system. When you have one phase that is dispersed in another one. It's a very important part of soft matter. So you can have emulsions, water in oil like in butter, or oil in water. So you can find in emulsions, in food, a lot of foods are dispersed systems. In cosmetics, in many eco-materials. Why? Because, for example, you can disperse an interesting function in water. So you can make a material that's made of water. And industries like it because they can disperse air. So what is nice, if you disperse air in a liquid, you can sell a very small amount of liquid for very expensive because mainly you put air inside. And many ice cream, actually, they put air also inside so that what they sell is actually a very small amount of material with a lot of air inside. So in terms of properties, they are very rich in interfaces, which make a lot of transfer very easy to do. They are water or air-rich materials, which is very interesting to develop, for example, biomaterials or sustainable materials. And here, all these dispersed systems, they can also be used to make microcompartments. So it can be drops. You can do, for example, polymerization dye drop, and a lot of macrofluidics is done with droplets, especially for applications. You can do a lot of you can miniaturize with macrofluidics. You can do polarization, screening. Here, for example, there is an example where you saw droplets and you can identify new proteins or new enzymes. Okay, so next part of soft matter, I would like to talk about drops and bubbles. So I made part of the job for you. I already say what it is. So what is this? It's rain. And where is it? It's here. Yesterday at lunchtime, we had this beautiful rain in the campus. I'm sure we'll have more during this week. So it comes for a sudden and then it disappears, but it's very strong, very impressive. So yes, so you can have rain, and I show here very interesting rain dynamics, and I can tell you that is quite interesting in terms of hydrodynamics. So you can find drops and bubbles a lot in nature, in raindrops, also inside our cells. I don't know if you know, but actually in most of our cells, people have recently discovered that we have a lot of droplets. So we have some macrophase separation, so we have some liquid-liquid phase separation, and we have a lot of compartments that actually in cells without any membrane. And this is due by phase separation, and this is due by creating droplets directly in the medium. And even in our cells, we have, like here you can see all droplets that are in our cells, and they are used, for instance, for energy storage. It's very important if you want to keep energy, to store energy in the form of fat in the cells. And look at this beautiful animal. I don't know if you know this spider. It's called Ardioneta aquatica. This is a very interesting spider because it's a spider, it's an insect, so it breathes, it lives in air, but it's a very shy spider. So these spiders, most of her life, will go inside water and make a bubble and will live inside the bubble. Okay? But this spider has to find food. So the spider has to go outside, take some insects, and then bring it back in the bubble, okay? And in the bubble, she will do the baby, she will mate, and she will do all her life in this bubble. So I think many of us maybe dream to live in a bubble, but this spider can do. And if you think about in terms of soft matter or in terms of material, it's quite something difficult to do because this spider, imagine she's in air, and she has to be able to cross the air-water interface to go inside water. Okay, so we could think to make it easy, she should be, for instance, hydrophilic because she's in air and she has to go inside water. But once she's inside water, she has to create another interface because she has to enter inside her bubble. So now she has to go from water to air. So to do that, we should see if I want to go from water to air, it's better to be hydrophobic. So you see that you kind of have something quite very interesting in terms of material because she should be able to cross water interface from air to water, but also from water to air. And this exists in nature, and these are quite interesting. And of course, we are all familiar with bubbles, which have these all beautiful transient shapes. So mainly all the systems are surface tension driven and will be in competition with mainly inertia, viscosity, and gravity, basically. And they are very rich in terms of shape adaptability, you see, and dynamics, if I take the example of the rain, for instance. And another important components of soft matter are membranes. I show you some examples here. Membranes are very important. They are the walls of life. They make compartment in life, and they make possible that things are organized. And you see that they make all the architecture of the cell. So it's membrane that make possible metabolism. Otherwise, the metabolism we have would not have been possible because everything was just mixed up. And if you look at the membrane itself, it's a very interesting soft material because it's fluid. And at the same time, it's very functional. So we have a lot of components inside this 2D kind of liquid. And also, we can build membrane and make synthetic cells. And this is a recent example from my lab where we could create some synthetic cells where I can control the polarization. You see, we can make this phase separation and control where we put the domain. So they are very important property for compartmentalization, but they are also highly deformable. They are very soft material, they are permeable, and they have to be broken and fused many times in our body, and these are very typical soft matter properties. So we have seen a lot of objects within soft matter, and I think what we can conclude is that they are very diverse, they are multi-scale, we went from nanometer scale to the macro scale, and they are very ubiquitous. We can find them always in nature, we can find them always in our everyday life, and we can most of the time find them in industry. So soft matter is also about properties. And I would like to just show just 3 types of properties, not all of them, it would be too long, but also that will be a little bit in resonance with what we will talk in this course lecture. So Maybe we'll start with something easy. What kind of property here I would like to illustrate with these 4 images? Self-assembly. Yes, self-assembly. So I will show a different example. This is a self-assembly that we make in the lab using DNA. So we can take DNA and program self-assembly and make, for example, a smiley shape. These are DNA nanotubes that also it's from the lab we put in the synthetic cells and they self-organize to make this kind of dynamic artificial cytoskeleton. These are colloids, and why I will show in a lecture was interesting is because here it's dissipative self-assembly. What it means, it consumes energy to be in an organized state. So this organized state needs energy, like us, like life. Life is out of equilibrium, and life maintains itself by consuming energy. When we are at equilibrium, it means we are dead. So we need to be out of equilibrium to be alive. So self-assembly you will find everywhere in nature, from cytoskeleton of cells to very large scale, like fish schooling, bird flocks. What is very interesting in this thing is that each individual are just very local interaction. Okay, so each fish just see a few neighbors, but collectively you have a macro-scale organization. This is typical of active matter. So what is nice with self-assembly, we can have bottom-up self-organization. So we can have things that self-organize. Here, my DNA, I didn't take each DNA by hand to build this shape at a nanoscale. This DNA, just by local interaction, will by bottom-up be able to reach, in this case, a nanoscale organization, in this case, microscale organization. And what is nice is many times this assembly will bring new properties, like cytoskeleton. If you take a monomer of actin, it has nothing really interesting. And when it is self-assembling, then you have a cell architecture. And also, properties, what is a challenge with self-assembly? 2 challenges, and 2, I think, quite interesting, is first kinetic traps. Because you have local interactions, but if you just usually, you have a very complex energetic landscape, and many times you have a high risk that you are just kinetic trapped somewhere. So I can tell you that this is self-assembling, but there is a high chance maybe that the system doesn't assemble properly. So this we'll talk about. How can we face this problem of kinetic trapping in self-assembly? And also reconfigurability. We can make beautiful self-assembly, but how can we make a self-assembly reconfigurable? How can we make, for example, a dog becoming a bird? Okay, like reconfigurability. So that's very 2 important challenges in self-assembly, and I think we'll talk quite a lot in this lecture. Here, rather easy, what am I talking about? Weighting. Yes, so you see here are some examples of weighting. You can see in plants, in insects, animal skins. This is a very interesting example. I don't know if you know this beetle, but this beetle lives in the desert, so water is very, very rare, and it's able to condense the very small amount of humidity, and this humidity will wet, and then this animal will drink the water it's collecting. So it's also used by people who want to catch, for example, water from the atmosphere to trap, for example, water from clouds. And of course, this very famous lotus effect we can see on many plants, not only on lotus. It works very well with cabbage, for example. And also at a more industrial or practical scale, it's used a lot for digital macrofluidics, using electroweighting, for instance. And you can also, by varying the weighting, you can make lenses with a variable focal length. It's used a lot in drones and in a smartphone camera, for instance. So you have a polymer, and we will change the weighting, and this will change the focal distance. So key properties, this is what will define the contact angle that can be static and dynamics. And in terms of challenge, you have to think when you deal with solid surface, you will always face possibility of contamination and pollution of your surface. So many cases, you can have beautiful theory of wetting, and when you go in practice, you can have problems. So it's always important to keep in mind that the surface is exposed to a lot of volume, so it's very easily contaminated. And also, very important are heterogeneity. It's very hard to get very homogeneous surfaces, and heterogeneity will give a lot of complex behavior, such as hysteresis, contact angle hysteresis, and part of the Hans-Hahn will do in this lecture will be about that. And here, I just show these examples. And here, what I'm talking about interfacial dynamics. So this is something we can also observe when there are beautiful phenomena in nature. For example, insects propulsion. So here you see a bug, a beetle. In this case, this beetle is not in the desert. It's a very common beetle that is walking on water. And if this beetle see a predator, like a fish, it will release surfactant from its back, and this will create a manganese stress that we'll see a lot in this test. And this manganese stress will propel the bug very efficiently, much more efficiently than using muscles. So it's very interesting propulsion, and it's purely interfacial dynamic effects. And these are also very interesting. So this is spider web. I think you have all seen droplets on spider web. And in fact, it's not so obvious, this droplet, and it's due to a very smart, or very interesting property, is that actually the fibers of the spider web, they are not cylindrical, they are conical. So when you have water wetting a conical fiber, you have a gradient of contact angle, and this gradient will create flows and transport. So what happens is that because it's conical, water will move along the fiber, and they will stop at this maximal diameter. So the water will be transported, and instead of having water everywhere, water will move and will just accumulate at specific points. So then the spiders know that it will always be able to find some space with not too much water. So this is if you take a conical fiber. So if you take a conical fiber and water on it, you will have transport from the small diameter to the high diameter. And now if you revert, if you now take a tube, a conical tube, now the gradient, now if I take a tube, and if this tube is as a gradient, now I have a gradient of confinement, it will be just the opposite, because now I'm confined. So if I have a gradient of contact angle in a confined tube, the liquid will go toward the smallest angle. And this is used actually in some birds. So use this beak, it will make an angle. Okay, and then the water will go inside by this gradient confinement, and these birds will oscillate the angle so that this system the equilibrium state will be moved by making a ratchet. And this is a very efficient way to take many, many, many small droplets at a very high speed and then to capture a lot of prey. So this system usually by using gradients or confinement or evaporation will create flows, and these flows can have very rich properties. And we have the examples also of the tears of wine, coffee ring effect, patterns, and many things you can have even in device like electrowetting device, what I showed you just before. And these are some examples from the labs with also some interfacial dynamics. By using wetting dynamics, we can mix, for example, macrofluidics devices is used with light, and here it's used to make self-propelled droplets, where you have very interesting transport. So in terms of challenge, with all this interfacial dynamics, what we will always face is that, okay, soft matter is cool, soft matter is everywhere, but soft matter is also a lot of phenomena together. So we'll have to deal with complex systems and usually with a lot of multi-scale and multi-parameter problems. That's something that will be quite challenging in many cases. So we saw that soft matter is also about phenomena and properties, and I think there is a lot of interesting and useful phenomena, and realize always this challenge of how can we understand it, and also how can we control it. Okay, so far so good? Yes? Okay, so now we have seen, I tried to give you a definition of soft matter. I try to define soft matter by its components and also by its properties. So we see that, what can we say? In terms of components, it's diverse, it's multi-scale, going from nanometric to macroscopic scale, and it's everywhere, it's ubiquitous. And also it's in terms of components and in terms of properties, we have a lot of interesting and useful phenomena, and we have quite this challenge of how we can understand and how we can control it. We see a lot of objects, we see a lot of phenomena, and it would be great if we could give like a universal formula to describe all of these things. So you know, of course, that in the past century, Albert Einstein gave this simple equation that could explain a lot of things, right? So the question is, could we find such an equation to define soft matter? Okay? It's something quite interesting. You know, I show you a lot of objects, I show you a lot of phenomena. Many are some are usual, some are curious. Is that such an equation? So, could we find a way to unify all these things? So we have this great diversity, like life. Life is diverse, but at the same time, there is unity in life. You have some common law. So, can we find something common in all these objects, from nanometric organization, colloidal assembly, dynamic assembly, forms, interfacial rich materials, electroweighting, gradient, confinement, interface, interfacial shape, self-propulsion, interfacial dynamics, self-organization, synthetic cells, hydrodynamics, rains, drops, bubbles, transports, synthetic cells, phase separation. What is the common point of all these components and this phenomena? That's quite interesting question, right? So I think there is a formula I can write, and this formula is not E equals mc to the square. It's very similar, actually. The formula I propose is very simple. It's E close, similar to kT. So this is the thermal energy, and in all these phenomena, you have either the typical level of energy of interaction is usually on the order of the thermal energy kT. Hydrogen bonds, electrostatic interactions in water, hydrophobic interaction, typically we are at this scale, but also processes with adhesion will work typically at the thermal energy. So it's quite interesting that in all this diversity of phenomena, we have this common point that everything I will look at will be something that has typical energy that is comparable to the thermal energy. And then we have something that is quite interesting, because we have these diverse objects that are very familiar, that are so different, but they have this common point. So we can find some common laws in all these very different objects. And I think it's quite interesting from a scientific point of view, from a physical point of view, to say, okay, this is very diverse, but there are some common laws. And also it's very satisfying, you know, because you can work one day with making DNA origami, and the other day making droplets, and maybe another day study how spider can live in a bubble. And we also have a lot of interesting phenomena. Some are very useful, some are just curious, and it's nice because maybe when we learn here, maybe we can apply and use it later to understand this, okay? And because most of the systems are comparable to the thermal energy, this makes soft matter very responsive. So you don't need to pay a lot of effort to have a response. This is the example, for example, of liquid crystal. You take a liquid crystal, you just put a little amount of electricity, and you can have a phase transition, and this phase transition will change the color. And with this, you can make a screen, or just a change of temperature. And life works because it's it is typical energy, and we have systems that are very dynamic. Because if the energy was much below kT, everything will be frozen. Okay, it will be static. And if everything would be too high, like 1000 kT, it will be like a gas. So, okay, dynamic but disorganized. So we are just in between. We are between something too solid and something too disorganized. And because we are at this level of energy. And finally, what I like in soft matter is, in fact, it's a bit messy. Okay? You have messiness in soft matter. It's something always a bit disorganized. And I think it's quite interesting in terms of research when you work with something messy, is because you will never control everything. And if you don't control everything, it means that you have a lot of chance to get surprises. And that's why it's a very interesting and cool field of research, because you can work on something like a foam, for example, and discover something. You are already prone to discovery when we do soft matter. It's like when you do archaeology. If you go to Egypt, you have a lot of chance to discover something super interesting. And in soft matter, we are this because you have this messiness. So it can be a bit annoying sometimes because you work with a drop. It's very simple. You will do some experiments in the lab. Maybe you will have failures, a lot of failures, and it's a bit frustrating. Okay, I have a drop, I put on something, and I fail my experiment. So I have no excuse why I'm doing something simple, it fails. But at the same time, okay, it's a bit sometimes difficult to control, but sometimes you can discover many things with simple systems. So this is what I find it quite interesting with soft matter. So something I would like to state is that we are soft matter. We are, all of us here, soft matter. So this is me visiting yesterday Subramanian's labs with all the great teams and all these volunteers helping us for this conference. We are all soft matter, and you are part of soft matter, as well as these dogs waiting for my talk yesterday in the front of the building. They are also soft matter. And this beautiful tiger from India is also soft matter. So I would like to ask you why, after all I have said up to now, why can I say that we are soft matter? Why I can say that living systems belong to soft matter? I would like you to answer this question now. Why can I say that we are soft matter? We, all of us.
As for some feedback, the system in this atmosphere, New York, like our bones, and like everywhere, our cells, everywhere there's self-assembly.
Yes, that is part of self-assembly. So that's part of the answer. I put two answers, and I think this is part of the two answers I propose. Yes? So just to say that there will be some awards at the end of this lecture. So if you participate a lot, maybe you have a chance, a better chance to get the award. I don't know, but there will be awards. So if you don't get the awards, it doesn't mean anything bad, but if you get it, it's great, okay? So, yeah, so the answer is part of the two answers. So what else? Why can I say that we are soft matter? We all living systems are soft matter. Yes?
So, is it because like soft matter is so diverse and living
Yes?
systems also is diverse but then unified?
Yes, so this is more like it's similar, it looks the same. But we can go a bit more than that. We can say that living systems are soft matter. Yes.
So, is it about self-propulsive nature?
Self what?
Self-propulsive nature. Self-propulsion. Propulsion.
Self-propulsion, sorry. So self-propulsion is a property. So yes, we can find some like self-assembly, self-propulsion. I think this can be categorized as one of the answer. And if we think there is a bit more than that, but yes, self-propulsion is part of it. And what else? For example, remember what I talked at the beginning about the components? Yes?
So what are surfactants we have all inside us? We have
Yes.
proteins.
Yes,
we
exactly.
have,
So
polymers.
exactly. So
And
I
we are
think
not,
yes.
and we are not that too solid, and we are not too disordered. We are in between. So
We are very in between, yes, because if we were too solid, our life would not be possible, and if we were too hot, we will be totally dispersed in the universe. So, agree. So I think we can answer these questions. Yeah, you want to answer? Yeah, go ahead.
Yeah, I think these all examples have one common thing. They are dynamic in nature.
Yes.
They are stimuli responsive and out of equilibrium.
Yes, and I think all the answers you gave are correct, and I think I can categorize into two parts. First, living systems are made of soft matter by composition. By composition, we are made of polymers, membranes, dispersed systems, oil in water. Our solvent is water. We have liquid crystals in our DNA. We have interfaces. We have colorants. We are made of soft matter. So by composition, living systems are soft matter systems, just by composition. And the second reason is that most of biological process work at the thermal energy KT level. If you take ATP hydrolysis, if you take molecular motors, if you take hydrogen bonds, if you take all the forces, all the processes, all the chemical process, all the chemical potential that biological systems are working with, all of this at this KT 10 kts, maximum 100 kts level. So, as you said, we are in this in-between range of having processes that are not at too low energy because everything would be just frozen and not reconfigurable, but also not requiring thousands of kT. Otherwise, nothing will be possible. So, soft matter, living systems belong to soft matter by composition and by properties, just by what I tried to introduce at the beginning of the talk. So far, I show you a way that we can introduce soft matter by showing you components and properties and living systems that are part of soft matter, and also trying to give you a unified view of soft matter, how we can find diversity and unity in soft matter. So I would like now to take the last 30 minutes to discuss with you about the objectives of this GIAN lecture. So these are two special animals. They are my dogs. In France, we don't have so many free dogs, so dogs are not really free, unfortunately, like here. But these are my two dogs on a beach in the north of France. It's colder than here, but you can have some beautiful beaches as well. And you see, if you look at these two entities, soft matter entities, I found it amazing. They can move, they can interact, they can adapt, they can change a property, they can communicate, they can sense the environment. And of course, these are not just running, but they can even reproduce, they can even consume energy to do something. So it's incredible, amazing in terms of properties. And I think as scientists, we can ask, but how can we understand this behavior? That's very challenging, intellectually speaking. But living systems are so complex. If you ask a biologist, can you explain me that? This biologist will be a specialist of very specific process and will say, okay, this is two things, and you have hairs and you have skin, and inside your skin you have a lot of things, but at the end I will be lost, I will not understand what I'm talking about. So living systems are very complex, but because living system is part of soft matter, and because we have laws, because we have some common properties in soft matter, maybe we can use this knowledge to approach and understand a bit how they are working. And also, if I look this more as a material scientist, here it's chemical engineering department, it could be very nice to be able to build such material that is able to adapt, that is able to move, that is able to live without consuming oil, without burning oil, but could have interesting property in a sustainable way, could adapt, could self-reproduce, could we have materials that self-reproduce? That could be nice if we could make it. But I am a chemist, but if you ask me as a chemist to synthesize this material from scratch, this is very difficult. You can ask ChatGPT, tell me which components I have to order from Merck and what kind of chemical reactions I should do to synthesize such material. ChatGPT has a lot of power, but will be confused for a good reason, because we don't know how to synthesize this. But again, we have all this knowledge about soft matter, and we have this unity, so maybe it's possible to approach at least some of these properties with very simple soft and synthetic soft matter system. So we have this living system, very rich in properties and very complex. And we know that living systems are part of soft matter. So we know that maybe we can use the fact that we have knowledge, a unification of knowledge in soft matter to approach this problem. So what I think we can state as the objectives of this course is to say, we'll not make life here, but we can be interested by these lifelike properties. And we can try to approach them, like dynamic self-organization, sensing, reconfigurability, adaptability, motion, transport. All these properties that are also living life properties, we can approach, and we have concepts of soft matter to doing so. And because life is complex, we can just use here, in this talk, we'll not see any biology. We'll use everything, will be synthetic, very simple, with just a few components. And why it's interesting to have synthetic systems is because first, it's well controlled. So you know what you put in your system. So it's very interesting if you want to understand. If you want to understand something, you need to control what you put, so then you can vary a parameter and you can study specific parameters. So it's very interesting to use synthetic soft matter because it's well controlled. And then this is to understand, but to use as a property is very interesting from a user perspective, because if it's synthetic, you can adapt. You can customize it. And this is something you cannot do with life. You cannot customize life, okay? So that's why the objective is to approach these lifelike properties, but always use systems that are totally synthetic, that we know what we put inside, okay? And with that, I think we have two challenges that we would like to address in this lecture series. Is first, to understand how soft matter principles can lead to such lifelike dynamic properties. And I hope at the end of this week, you will have learned some of this, and you will have new ideas that even maybe we didn't think about it, okay? So we are here to understand. I think it's part of our quest as a researcher. And also to make, how can we, with our knowledge, with this knowledge, can we make simple synthetic materials, but that can have these very interesting lifelike properties, like reconfigurability, like dynamic self-organization, adaptability, motion. How can we make it as a kind of engineer? So there is this double objective to understand and to make. And I think it's quite interesting to think that we are in this context of, it's not biomimetism, it's not, but it's lifelike properties that we can do. And soft matter, I think, is the best framework to doing so. So I've showed you a bit of, I think it's very clear that living system, very dynamic. I showed you components, droplets, and so on. So we'll talk about actuation. How can we do something to have a response, and a lot of reconfigurability. So that's two of the important objectives of this course. So just, I would like to finish by a few last slides to look back at this slide of these two reading dogs. So, okay, we can use soft matter to understand this. We can use soft matter principle. We can use soft matter components, and we're trying to approach these lifelike properties and learn about, understand with principles, and make to try as an engineer try to build this kind of properties. But how is life working? Is life a soft matter physicist or chemist or scientist? I don't think so. Life is not a soft matter scientist. So how life is working? Just how is it working in life, actually? Life is not working by applying soft matter principles. Life is working with an alphabet, with a function, a toolbox of functions. And this toolbox of functions at a molecular level, if you take a big microscope, what you will see is that most of the functions of life are ensured by proteins. Okay? Most of our functions are from proteins. Immune systems, communication, energy, photosynthesis. You take photosynthesis, it's a protein in the middle. All functions are ensured by protein. Now, look at this protein. They are beautiful. I mean, I find it beautiful. They have shapes. But again, if you ask me as a chemist, can you synthesize me this with an organic reaction? It's very difficult. Because, okay, maybe I can put all the molecules together, but I have to make this shape. And this shape is dynamic. So not only I have to control the shape in space, but I have to control the shape in space and in time. It's also very difficult. So life is not working like that. Life is not working with a book of chemical reactions. This is just for metabolism. Metabolism is not so difficult. But this is the central of functions. And how life is working? Life is working with something very different. Life is working with a very simple molecule that is in the middle. And this molecule is DNA. What is quite amazing is that if you look at all these functions, each protein at a physical chemical point of view is different. They have different size, different shape, different hydrophobicity, different dynamics, different surface energy. So they are so different. But in the middle, you have the molecule that is DNA. This DNA is the same molecule everywhere. It's the same molecule in the dogs, in myself, in the tiger, in the bug in my guest house. This is the same DNA, the same chemistry, the same physics, the same molecule everywhere in all the living system. So actually, all these complex functions are programmed in a same molecule that is shared by all living systems that we know so far. So we have a program, and this program is DNA, and DNA is the molecular code of life. And it's quite amazing that it's the same molecule in all living systems, the same chemistry, same shape, same physical properties. The only thing that changes is the program inside, but this is the same molecule. And this is support of the code that will program all this function. And at the same time, what is quite interesting is that if you look, the structure is very simple. If I compare to a protein with very complex 3D shapes, this is very simple. It's just double helix, like a staircase. Okay, it's something very simple. So you see that in living system, in life, you have this. It's very simple, but you have this separation between functions and a program. Okay, and if you look, like the program is made of DNA. So program is made by a very simple molecule, very simple structure, and that is everywhere. This is highly conserved. And functions, on the other side, are ensured by very complex molecules and very diverse. Okay? So I think living system, you have this interesting concept to separate functions from program. Okay, so a living system will not try to build properties as we do usually as engineer or chemist. Usually what you do when you want a property, you will put different components and you will mix until you get the property. But life is not working like that. Life is not working by putting many things together. Life is putting all the information in the same molecule in DNA. And if you look at the soft matter perspective, what is interesting is both the program and the functions are soft. They are soft materials, they are polyelectrolytes. DNA are polyelectrolytes, proteins are polyelectrolytes. And they are subjected to soft interactions, hydrogen bonds, hydrophobic interactions, electrostatic interactions, pi-pi interactions. All these interactions are soft interactions. So why is it important? For DNA, for instance, because it's a polyelectrolyte, this ensures the DNA packaging. It's electrostatic that ensure that DNA that has a lot of information can be stored in our cells. You have to imagine that in our DNA, we have this code, but it's 2 meters of information. Okay, so you have 2 meters on a molecule that you have to put in a cell nucleus that is 1 micrometer. So you need to package this information. And you can package this information because it's a polyelectrolyte, because you can use electrostatic interactions to package these 2 meters of information in the DNA. And at the same time, because you have soft interactions in the DNA, because it's held by hydrogen bonds, you can with weak with not so much energy, you can separate the DNA and you can reassemble it. You can melt the DNA and you can hybridize the DNA with not so much energy. And this is the basis of information transfer. It's because you can separate the double helix and because you can reassemble that you can transfer your genetic program to your progeny. So it's a very essential component of life. So you have a code, and this code can be transmitted to the progeny, and it can be mixed by another one. And this is diversity of life which is working like that. And this is because DNA is a soft material and a soft interaction. And the same for proteins. Proteins, because they are polyelectrolytes, they can have interactive, they can recognize to each other at the level of between proteins. And because they have soft interactions, they have this very dynamic conformation. And this is the essence of protein functions. Protein functions, their property is not so much by the amino acids, but it's very much into their dynamic conformation, like enzymes. Enzymes work because they have specific shape and specific dynamics. So you see that the two components of living systems are soft materials, soft interactions, and they have this way of being built not by formulation, but by programmation. Okay, by have a program that will control this function. And that's why in this lecture series, our objectives will be about actuation and reconfigurability, which basically all the things I showed at the beginning. We have this rich dynamic behavior, we have soft matter principles that help us to understand, that help us to make. And to that, I would like to add this programmability. Because you see that life is not done by formulation, but life is done by programming. That you put all information in a very simple molecule, highly conserved, that is DNA, and then this can give this huge diversity of functions through the protein. That's why in this lecture series, I would like to share with you this idea of programmability, actuation, and reconfigurability. So I will finish just by telling the outline and what will be our menu. Today, we have a rich program. So first day, introduction. This is almost done. It will be followed by a lecture on weightability switching. So we'll start to go a little bit in the hardcore of soft matter. And then you will have some laboratory hands-on from this afternoon. Tomorrow, I will speak about programming. I like programming, as you saw. And in the context of mimicking functions like synthetic biology, how we can program some properties and soft materials in the sink. We'll have a lecture about liquid marbles. Marbles are something we can play with it, and liquid marbles too, and they are very rich in terms of physics and properties. And we'll have a second tutorial on tomorrow afternoon. Day 3, I will speak about programming, in this case, nanostructures, and it will be a lecture about what we can do with DNA nanotechnology. And we have a second lecture about slippery surfaces, so dynamic on the surfaces, about mimicking the nature, but also how to see some new surfaces. And we'll start with a challenge. It will be the part 1, and we'll start with the part 1 and not with the part 2. We'll explain you later. Day 4, I will speak about soft matter actuation and how we can make microfluidics controlled and programmed with light or with magnets. Then it will be followed by lecture on soft matter micro-optics, how we can build like live living optical device. And we'll have a third laboratory on this day 4. And on day 5, final lecture will be on colloids, on interface. And I will show you how we can use some soft matter phenomena like coffering effect to do medical diagnostics. And I will also show you how we can have crystals that can be alive, like organized crystals that can be alive, like living systems. And in the last lecture will be about curvature-driven assembly in soft matter, and with this idea to go to reconfigurable materials and probably soft robotics as well. And we'll have the second part of the challenge. So about the tutorials, it will start this afternoon. There will be 3 topics in rotations. You will be separated into small groups. Basically, each session you will work on one topic. So each of you will work on 3 topics in total. These topics will be about soft polymer surface and weightability. Another one will be on the particle drops at the liquid interfaces and the coffering effect. About the challenge, we will work on this challenge in the context of soft DNA nanotechnology. So on the part one, I will give you the challenge. You will work in group, develop your project, and prepare a presentation to convince your colleagues that you have the best ideas. And in the second part of this, you will present, we will make a debate about it all together, and I hope it will be both fun and interesting. So with that, it's probably, yeah, I don't know, it's finished. So thank you for very much. We have a few minutes if you have some remaining questions. We already interact a lot. I think there is one question there, over there.
So is all viscoelastic materials be considered as a soft matter?
Yes, of course. As soon as they are not too solid and they are organized, yes. What I would say, viscoelasticity is one characteristic that we can study. For instance, when you speak about viscoelasticity, we speak about rheology. So rheology is a specific way to address questions and problems, like, for example, polymer chemistry can be another way, or like optics and so on. So we cannot cover everything like during the talk, but yes, these materials are class of soft matter. And what is interesting is that as a researcher, as you are, and as future researchers, what I think is interesting is that soft matter is a way, is a field in general where you can easily switch subjects, and you can decide to do rheology all your life if you like it. I found rheology very difficult, very difficult. In terms of, for example, formalism. The formalism in rheology is it's another language, you know, like it's for you in India, when you go to a new state, there is a new language, and it can be difficult. But some people love it. But what is nice is in soft matter, you can do rheology, and then you can go to something very different. Maybe you will work with insects, foam, colloids, whatever, and then you can apply this concept because you have these links between the objects. This is what is cool with soft matter. So then you have a choice either to continue in a very specific field all your life, and that can be great, or more to explore different one, and that can be great as well.
Yeah. So as we already discussed about emulsions, so what about the suspensions?
Yes.
Suspensions are also
Yes, suspension, I think I mentioned at the beginning. Yes, suspensions are very well soft matter because you have objects that don't sediment, and they don't sediment because they have enough Brownian motion. So Brownian motion is a fundamental component of soft matter. And yes, suspensions are very much soft matter, and they have a lot of very interesting behavior.
Thank you, sir.
Okay. So I think it's very nice that to have experts, and I think it's always a choice. So you can either explore many things and then see experts when needed, and for example, interact with you as an expert, or you can, once you have a love at first sight for something, and then you will stay in this specific field for, and then you can go deeper and deeper. So then you can choose, because really, I'm going very, very deep in something, and then it's very interesting. Or let's say, okay, I dig a bit, and then I will dig a bit later forward. So that's what is nice with soft matter as well. You can choose exploration or digging very deeply in a specific or in a field.
Thank you, Professor Bagel, for the wonderful talk. So
Thank you
I
very
have a
much.
question.
Yes?
Yeah, so soft matter systems are mostly driven by entropic forces, right? So
Yes. Depends.
in the case of self-assembly,
Yes.
they are forming ordered structures. So the entropy should increase, right? So usually in thermodynamics, we say that is a system goes from
Yes.
higher entropy to lower entropy. So in the case of self-assembly,
Yeah.
what could be your comment on the entropic forces?
Yes. So entropy is a bit tricky because we don't really know what is entropy. And sometimes you can explain everything by entropy. So because in any system that is organizing, you have disorder that is created, so you can always find. So I like to be careful with entropy because many times it's used as a big words, and you can say, "Oh, this is explained by entropy." Yes, of course, because anyway, I think we can believe the laws of thermodynamics. So entropy is always increasing. There's no problem. But then in self-assembly, this is a very important question. Self-assembly, we will have I will talk a bit about that. But you have two objects, and they have some specific, like just very simple rules of interactions. And in self-assembly, usually what we deal is that we have a lot of copies of this guy, for example, these two guys. But I can also show 3 components, or 4, or 5, and then it becomes very complicated, especially if you have a large number, you have a lot of collection. So then, if I look at the thermodynamic point of view, the energetic landscape will be very, very complex. Very complex. In many situations, we don't even know what is this energetic landscape. And you start by something high energy, and you will go down. There is no choice. You will go down in energy. But the big challenge are the kinetic trap, because when your system is in a local minimum of energy, how this system can know that the actual minimum is there. And this is a very big challenge in self-assembly, is to deal with how you make your system to go to thermodynamic equilibrium. But sometimes you don't want to be at thermodynamic equilibrium because you want the system, for example, to be reconfigurable. If you want the system to be reconfigurable, if you force to be at thermodynamic ground state, it will not be reconfigurable. So that's a very, very important question in self-assembly. So for me, I would say that rather than entropy, I prefer to consider whether it's under thermodynamic or under kinetic control. And thermodynamic control means that the system will be able to reach its free energy minimum, which takes into account enthalpy and entropy. Or you are controlled by kinetics, meaning that sometimes you have some interactions and the system is frozen and cannot escape from it. And it's not a problem of entropy or of whatever. It's just that it cannot escape because the energy barrier is too high. And in this case, it will be controlled by kinetics. So for me, this is more, what is very important is that whether you have a system that is controlled by thermodynamics or a system that is controlled by kinetics. One aspect. And the other aspect is equilibrium versus out of equilibrium. And it's nice to work with system at equilibrium because you can predict, you can control, and it's very nice to manipulate. And at the same time, you have living systems that are out of equilibrium that also have interesting properties. And so that's why there's very important questions about self-assembly. What I found a good way is to consider either you are under thermodynamic or kinetic control, and they are all competing. Kinetic traps is a very important challenge in self-assembly. And the other one is equilibrium versus out of equilibrium system. So that's what comment I could give on that.